Now let's show material flow, coffee bean grinder. Again, I can go in the kitchen at ITASCA. We had this coffee bean grinder a while ago, and someone had to put this word on there. Don't stick your fingers in there, because what? Oh, finger guard. Oh, what the hell is a finger guard? We're going to look at that. We're going to model this. Okay, we're going to model this system both with and without a finger guard. But before that, we need my famous coffee quote. I like this. I think this is the best quote about coffee I've ever seen. A mathematician is a device for turning coffee into theorems. I think that's I love that. I love that quote since I drink a lot of coffee. So what did we do to model these coffee beans? We used clumps, okay? So clumps are this collection of overlapping spheres, okay? What we can also though do is we can provide a faceted surface description, and we can use that surface description to compute the inertial properties of this thing. So what we then have is the inertial properties, the way it spins and all that kind of stuff. Remember the moment of inertia tensor, all that thing? Those properties are coming from this shape, but the actual contact detection and everything is this. Okay. Well, that's what we did in this. So here's the coffee beans sitting on the top. There's a hole there. Here is the finger guard, the top view and the side view, right? Okay. When we run this thing, we find, in this case, with no finger guard, we get uniform radial flow, which we'll see here from the side and above. Here's the top view. There's no finger guard. There's just a hole there. And you can see a pretty nice uniform flow of coffee beans going in there, right? And then we just remove them once they get down here. We weren't concerned about that in our model. Okay. Here is now the flow field with the finger guard. And look at this thing over here. There's this big giant stagnant zone. It takes a long time. It's like they're flowing down here for some reason, and they're stagnant over there. Sometimes it's so stagnant these don't even make it down through there with that finger guard. Stagnant zone on the left side. Why? Think of this as a 3D problem, okay? This finger guard is not just a planar structure. It has these vertical supports. Those supports are going to hinder the flow. And you see it right here. Right there. Those bloody supports are on the left side. And so therefore they're blocking the flow down here. And that's why it's the right side where it can just go through these holes over here, but here it gets impeded, right? So again, this is like a dead simple model. If you were just doing granular flow with PFC, it would be quite straightforward. All you got to do is build the geometry of the walls, make a collection of particles from some size distribution, create them, and turn on gravity, and just let her rip. But because we're building bonded assemblies, there's going to be some additional steps. We're going to have to pack them to begin with. Then we're going to have to put on some kind of a cement. And then we're going to have to do tests on it that we typically do, right? Whether it's a boundary value problem like rock cutting, or whether it's typically what we do is we build these assemblies and then we do direct tension and compression tests, and then we calibrate. We go and we choose the micro properties to try to match the particular, say, Young's modulus and UCS of a rock, right? Okay, that's material flow. Now, next one. Material flow. Rock slide. There's an example application, talks all about this in the manual of PFC 7. This is slide mountain. I don't know the length scale. Terrible to have a plot without a length scale. I just realized I don't have a length scale. This is big. This is probably a kilometer or more. And there was a big landslide in 1983, and you can see the remnants of that landslide. I don't know. They must have renamed the mountain. They call it Slide Mountain. The guy Matt Provence, who did a lot of the development of PFC 5, where he lives around here, and he sees this outside his window. So to do a demonstration of the power of PFC 5, he said, I'm going to model Slide Mountain. So the first thing I need to do is I need to have a contact model for what happens when you have granular flow. And there are people who model landslides with DEM, and they have developed a special contact model whose main parameter is restitution coefficient. What it is if you have a particle that's smashed into a wall, you have velocity in and then you have velocity out. And the ratio of velocity out to velocity in is restitution coefficient. It's a way of removing energy, right? Some particles, the velocity in is 1 meter a second and the velocity out is like 0.9. So that would have a high restitution coefficient, right? So that's what that is. And so that can be input to a velocity model that's handling these collisions. Okay, so if you then vary the restitution coefficient, so for example, it's only 0.1, so the velocity out is only 1/10 of the velocity in, there you go. It just does this. Okay, if you have a higher restitution coefficient, it bounces more. Look at this guy bouncing, it's pretty cool. Okay, this is again this representation for a clump. This is the outer surface description of that shape. And so that's being used for the inertia tensor. And that's why it does the proper bouncing. Watch this thing bounce around now. But there's really only one pebble in that clump. There's just a big sphere that's inside there. But notice how it's doing the proper motion because it has the actual inertia tensor of that particular shape. I love this picture. It's so cool. So then if we take a pile of those and we start at the top and we do the same thing with different restitution coefficients, this is the one with very little bouncing, right? And then you obviously understand what this is. This is a PFC wall with a bunch of triangular facets. There's gravity on. These guys were in a box up there and now we're letting them rip. So this is with very little bouncing. It's almost kind of like a fluid. They all stay together, right? And then eventually they're going to stop. There's a few guys trailing, right? If we do the other extreme with very high amount of bouncing, this one is probably not realistic. You can see how things are running out ahead. Don't worry, the camera where we're standing, we're lucky. We're not going to get hit by any of these. Whoa, look at that one. And so if we do this one, which seemed to be the best, this one is going to be much more realistic with the 0.3 restitution coefficient. And we're going to say that it's realistic because we're going to look at the final distribution of where everything ended up. And so again, from the literature that uses this contact model, talks about rock slides, the 0.3 seem to give much more realistic distributions, right? When it bounces a lot, they get a lot farther out. Okay. So there we go. Another material flow. Oh, and just to show a sexy one, this is a coupled model where we can couple PFC 3D and FLAC 3D. FLAC 3D has shell structural elements. So we can model a membrane as a shell structure here. And red is the deformation. So you can see they're all piling up and they're bouncing off of this thing. So again, this is a coupled model. We can do both. A lot of times we'll couple these bonded particle systems. If you remember the stope at the South African gold mine where we were advancing the stope, that was a PFC bonded system inside of a bigger continuum. So we can do that quite straightforwardly now with both PFC 2D and FLAC 2D or with PFC 3D and FLAC 3D. Okay. Enough said.